changed the bulb, but they didn't clean the filter. I swear to God, that clean filter message has been up there for years.
We can clean the filter right now.
Hmm?
We can clean it right now.
I don't know.
Is it like a
I don't know what
filter?
filter-
Just
I don't know what
replace
filter is.
it.
I assume that's what you
analysis of the filter.
All right, I have four of you have submitted your data for the disk equation work that we've done in lab for the last 2 weeks. Yes?
I emailed them to you.
Yes.
Did I do it right?
Haven't looked at it yet. I assume you did it right.
Okay.
Why do you think you didn't do it right?
I just wasn't sure. I was like, well, it's just an Excel file, so I guess I just type in
Type
the
in your
numbers
data.
and email.
Under your
There's
name?
like, yeah, there's like 3 different tabs. We don't do anything on the last tab. We can
No,
find
that's
data.
for me. Cool.
Okay.
And actually, this is an Excel spreadsheet left over from a long time ago. Ultimately, we're not even going to be generating our figures that way. We'll generate them in R.
Then why, like on our own worksheet, there are 3 columns. Why do we even use a 3rd column if we only enter the first 2 in the data?
What's through?
It's just dividing the
Division.
data divided by.
You want us to divide it, don't you?
Well, because you have
That's
to
the second
know.
column,
Yeah.
or the first.
So on the worksheet,
Mm-hmm.
so you have
Yeah, you want
total
us to
handling
divide.
time and you have handling time per prey item. You can't measure handling time per prey item unless you also have handling time.
Right, but like
That
when
way
we
it
enter
is
in
so much
Excel.
quicker.
I think we should-
You're supposed to enter the divided one into the
So
Excel
divided
sheet.
one into Excel.
The way it is now.
Okay, then redo it and, yeah, so the,
Because it said like number or like.
yeah, the things that I want is I want the count of how many discs you collected.
Right, which would be like 4, 12,
Count.
whatever.
And then I want the handling time divided by the number of prey items that you collected, which gives me the average handling time per prey item in that particular data. So those are the 2 things that I need.
Disregard.
Glad we had that conversation. All right. We're talking about economic decision-making. We started talking about the Golden Corral last time. Before we talk more about the Golden Corral, do you have any questions on what we did last time? Yeah, ma'am.
Okay, I understand the Starling concept, but I still don't understand how the graphs represent the concept.
The Starling?
The Starlings picking up the worms, and it's like the little.
Diminishing return.
Yeah.
The load?
Yeah, I just, like, I
Is
get
there-
the concept, but I just don't understand how the graphs illustrate the concept.
So, this is the general relationship between how many, given a certain amount of time that you have to forage for worms, this is how many worms you would pick up. And so in theory, you can just keep foraging and get more and more and more worms, but of course, the more worms that you have, the heavier you are, and since you're flying, weight is a problem. Also, the more worms that you have, because you're a bird, you have them all stuffed in your beak because you don't have hands, because your hands have magically, through evolution, turned into wings. So you also have an issue of how well you can control the worms that you have. And so there comes a point where you could stay and get more worms, but why would you, given the fact that you have to fly back to wherever you're going to feed, and also given the travel time. So generally speaking, the further away you are from the food that you're going to be gathering, the longer you should stay where that food is. Because when we think of models, and at the end of this chapter in your book, the chapter talks about, these are all optimality models. This is a general class of mathematical models. And these models all assume that you, the organism, are trying to maximize some currency. So one of the nice things about optimality models is that they make explicit predictions about what organisms should do, and these predictions are both quantitative as well as qualitative. So if you have an optimality model that is designed to predict the behavior of an organism, if your model is describing everything about that organism's behavior, you should not only get a good qualitative match of the behavior to what the model predicts, you should get a good quantitative match. We'll talk about how that almost always never happens here in a little while. But the other thing that optimality models do is it makes the currency explicit. What is it exactly that the organism is optimizing? Is it the rate of energy gain? Is it efficiency? You know, the amount of energy gain per unit time, for example. So there are lots of currencies that you can make with the dung flies. The currency is how many sperm you transmit to the female and how those sperm get translated into reproductive success of the male. So in this case, the currency is essentially what's on the y-axis. So as you spend time in this patch picking up prey, you are depleting the patch of prey. So as you deplete the patch, you saw this in lab yesterday, as you deplete the patch, it gets harder and harder to find prey. So the more time, this is time spent in patch, as you spend more time in patch, you get fewer and fewer prey. In this case, worms are unitary. You can either have 1 worm, 2 worms, 3 worms, 4 worms, 5 worms, 6 worms, 7 worms, 8 worms. But with each successive worm that you get, you've now depleted that patch so much it gets harder to find the next worm. And so what happens to your rate of gain of worms is the longer you spend in here, your number of worms per unit time goes down. Now, if your optimality model says that the currency is number of worms per time, this is a rate, this is the rate of worm gain, then where in this diminishing returns curve do you reach the highest rate of worm gain? You reach the highest rate of worm gain as soon as you enter the patch. The rate of change is always the slope of the line tangent to the curve. The more time you spend in this patch, your rate of worm gain goes down. And so if you're trying to maximize the number of worms that you gain, you want to spend as little time in the patch as possible because that's where the slope of the line tangent to the curve has the highest slope. So if that's your currency, then you should spend as little time as possible. But the only way that you should do that is if the patches that you're foraging in are very, very close together. Because where this line intersects the travel time between patches, basically intersects right there at 0, essentially. But if there's zero travel time between patches, it's not a patchy environment, it's a uniform environment. And so the time that you spend in the patch is then affected by the time between patches. The further the distance is between patches, the longer you should spend in the patch. What that means is your overall rate of worm gain goes down, but given that you have to travel a lot between patches, you're most efficient doing that because you have to balance time spent foraging with time spent in transit. And so, in this case, if the distance between patches is short, you should actually carry fewer prey because you can easily go from patch to patch or from patch back to where you're going to be ultimately feeding your offspring. But if you're further away because you're gone for a longer period of time, you collect more food while you were there, which means that when you finally do get back there, rather than have a little bit of food, you have a lot of food. And so the load that you carry is going to be affected by how far away, in this case, how far away the patches are from your nest. So the amount of time that you spend searching is determined by how long you have to travel to get to the place where the food is.
So you said if you have to travel longer, they're gonna carry more food with them.
Yes, so
But that's not the same as what the bees and nectar were.
these are doing a different thing, because they're maximizing a different currency. And so the currency that you're dealing with is important here. So what happens is, at short distances, you would have lower loads. At longer distances, you would have higher loads. And so what they did was they went out in the field, they trained starlings to feed from bird feeders. And if the starling's nest box is here, here's my starling, and you put the nest box, or you put the feeder out here, this distance is 10 minutes away, you could basically monitor the feeder, figure out how many worms they picked up from the feeder and brought back to the nest, and then you move the feeder 20 minutes away, you move the feeder 30 minutes away, and basically look at the behavior of the animals and say, how is distance from where their nest box is, how is that influencing how many worms they pick up? So in this case, these are the predictions. If you're very close, you would pick up 3. If you're a little further away, you would pick up 4. If you're even further away, you would pick up 5. Further away, you would pick up 6, et cetera, et cetera. So those are the predictions of this model, basically, as it relates search time to load. And then these are actually the behaviors, the dots are the actual behaviors of the birds when they manipulated distance to the feeders.
And why don't the dots, like, was there a rationale for why the observed isn't completely, like, with the predicted?
Can you save that question for a little while? Seldom do optimality models predict precisely the numerical value that will be observed. You're gonna see this over and over again in this chapter. In this case, the dots aren't exactly on the line. When we see this figure later on, here's the predicted result, here's the actual result. Qualitative match to the model, quantitative match is not exactly there. Over and over and over, you're gonna see this with optimality models, and there are a variety of reasons why. They talk about them at the very end of the chapter when they talk about optimality models. We'll talk about them at the end of class today, hopefully. So hang on to that question when we get to it. So, the bees. So, let me remind myself, because I screwed this up again.
Using the closer flowers are to other flowers in a nest, the more nectar they'll take at each load. The farther apart, the less nectar.
Yes, because what are they maximizing here?
The efficiency.
Yeah, they're maximizing efficiency, they're not maximizing the rate of energy gain.
Oh,
So-
why doesn't the shape of this look like the other shapes?
Because the y-axis, once again, is the number of flowers visited.
So is this a diminishing returns curve? Because it just looks like.
No, because this is not a diminishing returns curve, because this is the number of flowers that are visited. Each flower for a honeybee is essentially a patch, because there's a nectary there. I think I talked about this last time. There's a nectary there, and the longer you feed at that particular flower, the harder it becomes to feed because you're draining down the nectary. So in a flower, you guys know about Oenothera, the primrose? Primrose has a flower. It's a nice big showy flower, has big yellow petals. Well, if you look underneath that flower, you will see that there's a stem that connects the flower to the ground, but you'll also see that there's a tube called a nectary. Yeah, it's called a nectary. And this thing is filled with nectar to a certain level. When these things are fed on by hawk moths, the tiger moths, the moths that look like little hummingbirds, and they have a long proboscis that goes, here's the head, here's the thorax, here's the abdomen, you've got a big butterfly-like thing, a moth, and they have this coiled up tube of a mouth that they uncoil and send down this nectarine. And they hover there in front of it. One of the purposes of the nectar being that long is that the longer the nectar is, the further that you have to stick your proboscis down into it. And then if you have to stick your proboscis far enough down, your head is now making contact with the anthers and the stamens of the flower. And so that's how the plant forces the moth to pick up the pollen. But as the moth comes here and forages on the nectar, the act of foraging reduces the level of the nectar in the nectary, making it harder and harder for it to get more and more information, or sorry, more and more energy, more and more nectar out of the flower. So in this case, each flower is a patch. So you could think of your flower garden as a patch of flowers, and then that's different from a patch of flowers over here, and you could think of this as interpatch distance. You could put a travel time on that. How long does it take a bee to fly from this patch of flowers to another patch of flowers? But that's actually not a patch from a bee's perspective. A patch from a bee's perspective is this patch, and the travel time is the distance from that flower to the next flower. And so if you wanted to manipulate travel time, what you would do is something like we did with you guys yesterday. You would just actually reduce the number of flowers that are in a group of flowers. That now takes interpatch time that was this and lengthens it to that. So that then influences how many flowers you will visit in a given foraging bout. You will visit more flowers if the time between flowers is short, because your travel time is reduced. But as you gain nectar, what are you also doing? You're gaining weight. If you're gaining weight as you collect the nectar, because you're not actually feeding off of the nectar, you're actually gathering nectar to basically take it back to your hive and vomit it up for other individuals to eat. And so this isn't about your energy gain, this is about how big of a load of nectar you can bring back to the hive. So travel time is important because all that travel time, you're carrying more and more nectar as you go. If the travel time between flowers is relatively short, you're gathering nectar quickly, you don't have very far to go, and you're willing to take a larger load, which means that you will visit more flowers before you then head back to the hive. As the distance between flowers increases, whatever nectar you've collected at one flower, you have to now travel a long distance to another flower. That means that you don't want to be carrying that load very far. And so you're going to reduce the total number of flowers that you do, because the efficiency of you moving is dependent upon how heavy a load that you're carrying. An analogy for you that you might think of is when you go to the grocery store, you gather up your groceries, they put them in bags for you, and then when you go to your cart, you can take all the groceries at once because you have a cart to carry them in. And so it doesn't matter how far out in the parking lot you are parked, it's very efficient to just load all of them into the cart at once and take them to your car. Now you get to your home, and let's say that you live in a house like I do where you have an unattached garage. Now you have all these bags of groceries in the car, and it's some distance to walk from where you've parked your car to your front door. Now the question is, how am I going to get the bags out of the car and into the house? Am I going to load them up on Caleb is like, well, what you do is you put the one on your arm here, then you put the second one on your arm here, and then you put the other one on your arm here. But let's say that you're having a party, and all those bags are full of beer and soda and water, et cetera, et cetera. They're really heavy. You don't load them up all on your arms and try and get them all into the house all at once. You put a couple on there because they're heavy, you take them into the house, and then you go back to the car to get a second load. How you load yourself is going to depend on how far you have to carry them. Does that make sense? Of course, I don't usually entertain those kinds of decisions. I actually try and get them all into the house all at once, and my girlfriend's like, you know, you can make 2 trips. I'm like, no, I can do it. I can do it.
Efficiency trade-offs.
It's so accurate.
My hands are red from the blood being cut off by the bags hanging off my arms. It's like, no, I can do it. And then I get to the door and I realize my keys are in my pocket. And in order to get into my pocket, I have to move my arm, and then all the bags slide off my arm. It's a disaster. I should have just done what these did and carry a lower load and make more trips because the load is heavy. Does that help you conceptualize that? Sometimes a good human analogy works. Caleb, you're carrying them all at the same time, regardless of distance?
Always.
Yeah,
always. Efficiency is not my currency.
Efficiency is not your strong suit. So this is another example of be sure that you're paying attention to what the currency is that's being maximized in this case. People who write optimality models and aren't explicit about defining what the currency is, those models will oftentimes give you bad predictions because you haven't been clear about what that currency is that an organism is paying attention to. Prey choice. Prey choice, so in the same way that something like a diminishing returns curve can affect where you forage, these kinds of energetic decisions about how much energy you're gaining per time can affect not only where you eat, but what you eat. And so this is how I got onto the Golden Corral. And energy is in carbohydrates. You can get energy from protein, but you generally don't want to be digesting protein in order to get energy. For one thing, it's less efficient energetically, and the other thing is it reduces your body mass in an unhealthy sort of way. So just perish that whole protein energy thing. Not well founded in biochemistry.
It wouldn't make sense to just eat sugar 24/7, which is simple carbohydrates.
It wouldn't, but if what you're trying to do is you're maximizing energy gain, you want carbohydrates more than protein. What happens when you start digesting protein for energy?
Spend more energy.
No, so you get less energy out of protein because it
Goes fast.
has less energy.
It goes quick, right?
It doesn't go quick. It's a very
Protein?
slow source of energy.
Breaks down the muscle.
It breaks down your muscles, which is a bad thing. What does it do to things like blood chemistry if you're a human? Makes it more acidic. You go into acid. Ketoacidosis, that's the term that I'm looking for. And that's generally a bad thing. So, what's that?
Keto diet's real popular.
The keto diet is really popular, but that's a diet that people feed on that is probably good for people who aren't doing a lot of exercise. I spent an hour and 8 minutes on the bike last night, and at the end I was tired because it's on this virtual trainer. I use this program called Zwift. It gives you incentives for riding. And so when I'm riding inside for that hour and 8 minutes, because you're not outside, there's no opportunity for coasting, there's no opportunity to draft behind the people in front of you, et cetera, et cetera. So you're basically pedaling solid for an hour. You could go 2 hours, you could go 3 hours, you could go 4 hours. When I was in the, so I rode in the copper, not the copper triangle, I did that also a couple of years ago. I rode the triple bypass. The triple bypass is 117 and a half miles. It goes over 3 mountain passes. Maximum elevation was 12,000 feet. 2 of the mountain passes were over 11,000 feet. The third one was a mere 10,500 feet. And there were 10,000 feet of climb. So, what you do when you do this, what's that?
I would never,
You would never, ever?
ever.
Yeah, that's what I said once. In bicycling, they say that it doesn't happen if it doesn't appear on Strava.
Never heard that.
Yeah, because you don't ride a bike.
My mom does.
Makes a lot of assumptions.
My mom does.
I don't know, I'm not gonna lie,
My mom does.
I do.
Did your mom do the triple bypass?
She did,
Really? When?
like 3 years ago.
Wow,
It
good
was a
for her.
triathlon, it's a boy.
It's really hard.
What? It was a triathlon.
Yeah, they said they ate, like a whole pack of Oreos after. It's
Oh my God. So when you do a ride like this, you can basically eat whatever you want.
That was a pool. Dirty pool.
So here's my biggest ride.
My plan,
And peanut butter.
but without the bike ride.
You can do that, but without the bike
Yeah,
ride.
exactly.
So, this is the elevation profile. This is basically a 24-mile climb with practically no downhill on the whole thing. During this ride, what I'm doing the entire time is I am just eating carbs the whole time.
While you're on the bike.
Oh, yeah, yeah, I have a little, on the front of my bike, I have a little, on the front of my bike, I have a little pouch here. Oh, this is me.
Where are your
Um,
pegs?
Pardon?
Where are your pegs at?
My pegs.
Never mind.
I'm
Like pegs on like the kids' bikes?
Oh, yeah, no, this has no pegs. So this bag here is full. This bag here is full of basically hammer gel. Hammer gel is basically caffeine and sugar and very little protein, because what I want to be doing on this ride, and by the way, some time ago I was down there and I came all the way up this hill. This is going up that 24-mile
Where is this?
24-mile climb. It's in Colorado. The 24-mile climb. This is the last 4 miles of it. So on this ride, I'm just shoveling as many carbohydrates as I can get into my body, because what I want to do is I want to maintain my energy level, burning up carbs, so that I don't start burning protein or fat in order to make it through this. Because as soon as you start burning through fat and burning through protein, you start to get more acidic because of the outcome of that metabolism. And so you basically have water bottles full of sugar and salt, packets of gel that are full of sugar and caffeine, and you're basically just hyped up on all these things that are normally bad for you, but when you are riding 10 hours and 4 minutes, that's moving time. 10,551 feet of elevation. It is a historic effort, according to Strava. All you're doing is you're pumping in carbs because you're burning energy, and you want to keep your carb count, your carb titer up, because you want to be burning sugar rather than burning fat or protein.
You said protein like degrades your muscles?
So if you are so energy depleted that you start essentially digesting your muscles as a source of energy, then you're basically losing body mass that is not body mass due to fat, it's body mass due to.
I guess why do
Muscle
people
degradation.
like intake lots of protein after workouts then?
Because you want to rebuild, you want to, so your muscles are getting a workout, and one of the things that you do anytime that you work out is you stress your muscles, and as you go through the process of rebuilding, you want to provide your muscles a source of protein to build. Otherwise, you just stay the same size all the time. So if you are trying to gain muscle mass, you want to tax your muscles, and you want your muscles to repair themselves, and you do that by giving them protein to do that, to provide those building blocks. If you're a cyclist, you don't want to actually pack on a ton of pounds, because the heavier you are, the harder it is to carry all that weight up that 24-mile climb. Which is why when you see professional cyclists, what do they look like? They look like little string bean people, because they're very light. They have a very low fat percentage of their total body mass is made up of fat, because they are interested in minimizing weight rather than bulking up like a weightlifter or a football player or something like that would be. And so you want to have proteins on hand to repair any damage that you do while you're training, but during the act, what you're wanting to do is you're wanting to keep energy levels up, i.e. carbohydrate levels up, so that you don't do any more damage to yourself than you would during a normal workout. And what happens when you don't fuel correctly is you get to mile 52 and you bonk. That's what the act of bonking is. It's when you've depleted your simple carbohydrate stores, you've depleted your glycogen stores, and your body just doesn't have any energy. And so you can continue mentally pushing through that, but when you start pushing through that, you're going to start burning up fat and protein, and that's where things get really bad. Have you guys ever listened to the program Radiolab? You should listen to Radiolab. It's a national public radio program. They talk about science a lot. There is a program called Limits. So one of the episodes is called Limits. You should log on to Radiolab, listen to the Radiolab episode called Limits. It was one of the first episodes that they actually ever did. And one of the stories in that episode is about this woman who decided to run the Ironman triathlon, do the Ironman triathlon in Hawaii as her senior thesis. And she went and attempted to do the triathlon without really training appropriately for it. And during the triathlon, she really didn't fuel appropriately. And you can see for yourself what happens when you fail to train and fuel appropriately for something like that event. A triathlon is basically a 2-mile open water swim, running a marathon, and then biking 112 miles on a bicycle. No, but she lost complete control.
I hear she died.
She lost complete control over her body. And when I mean complete control over her body, I mean she lost complete control over her body.
Ah, perfect.
Yeah, everything. Everything, yes.
But on a scale of 1 to 10, like how bad do you feel after that? Since you are constantly recharging your body.
At 52 miles, I had just climbed 20 miles up a mountain that was an average of about 5% grade. And when I got to the lunch stop, which was 20 miles into this 24-mile climb, I got off the bike. I told my girlfriend, don't ever let me do this again. 2 of the 4 people that I went out to Colorado with to ride this with bonked and dropped out at that point. And one of them was sitting in the car trying to recover, but the other one was 10 minutes behind me on the mountain as I was pulling out to continue up the mountain. He was pulling in, and that was the end of the ride for him. So that next 4 miles was really, really hard because I was already mentally kind of ready to quit and give up the ghost. Once I got over that pass, that's Loveland Pass, you have a really long downhill to recover on. So at the top of Loveland Pass, I ate a bunch of carbs, I drank a lot, I hopped back on my bike and I coasted for the next 12 miles down the hill. And then I got to a place called Swan Mountain that's really not much of a hill at all. It's this little bump right there. Tiny in terms of elevation gain, but it was lower elevation, it was hotter, and there was a wind coming out of the north. That was the hardest part for me, was getting over that mountain. By the time I got to Copper Mountain, which is about right here, this last climb, it really didn't feel that difficult. Part of it was was I knew the route there because I had biked that path before. I had biked that route before, going up Copper Mountain to Vail Pass. This is Vail Pass. But then the other thing was, my girlfriend, she had a Snickers bar right there.
Not
Game
you and
changer.
No, no, she didn't give it to me.
Oh.
When I got
That's
down,
crazy.
That's a red flag.
when I got down from Swan,
She's, it's a red
I said, that's a
flag.
red flag.
it's a red flag. It didn't occur to her. I had a sandwich there that was packed full of protein, but I knew that what my body was needing at mile 52, my body was needing more carbs than I was capable of giving it, and a little bit of protein. And I had given her a Snickers bar earlier in the day, and I was like, do you have the Snickers bar? She's like, oh no, I don't think I do. So when we got down from Swan Mountain, there was a rest stop, and they had like candy bars there that had a lot of sugar, but also a little bit of protein. I ate a couple of candy bars there, and by the time I got to the base of the last climb, I stopped at a filling station and got another Snickers bar, and she was there waiting for me. And as I headed up that last pass, I was actually feeling pretty good because I'd finally taken in enough energy, sugar energy, to kind of get me over that last mountain. So when an organism is looking for energy, they're much more interested in carbohydrates than they are interested in protein. Hunter-gatherer societies tend to get a decent amount of protein. What they don't typically come into contact with is big pools of carbohydrates. So when they do come into contact with big pools of carbohydrates, like honeypot ants, what you generally do is you see them sit down with that colony of honeypot ants, they dig through it, they get all the honeypot ants that they can, they pop them in their mouth, they suck the abdomen off of it, throw the head and the thorax away, and they just eat all of that sugar. Because they tend to be in energy-limited environments when you are a hunter-gatherer. We do not live in an energy-limited environment because we can go and get sugar anytime we want. And that's bad for us ultimately, because we don't need that much energy. So unless you are doing a lot of physical activity, you should actually not be eating as many carbs as we typically do, because your body isn't evolved to do that. Your body is evolved to live on a lean diet that is relatively low in carbohydrates, because you come from an evolutionary history where most of our evolutionary history as humans has been as hunter-gatherers. It's only a relatively recent, in terms of evolutionary time, situation where we have this superabundance of food. So, you're at the Golden Corral. If your goal is to get energy, what are you going to do? Are you going to go and get the fried chicken or the shrimp or whatever, or are you going to get something else? You're going to go to the dessert pile,
Right.
assuming that net rate of energy gain is your primary issue. And this is where optimality models sometimes fall off. Maybe there is a situation where net rate of energy gain isn't actually the thing that you need most, but maybe what you need is the net rate of gain of amino acids, in which case you would make different dieting decisions, different decisions on the choice of what you ate. Now, within that, if you were interested in, once again, gaining the most energy and nutrients per unit of time, but you were at a end of the semester party. When I was an undergraduate, the biology club had an end of the semester party every spring, as actually an end of the year party. And we would drive over to Louisiana because we were near the Louisiana-Texas border, and we would load up a pickup truck load of crawdads, throw it in the back of the truck, bring it home, dump it in the bathtub, set up the boiler in the backyard, and just basically spend the weekend boiling crawdads and eating crawdads. What's that?
I said, we're lame, what are we gonna do?
Gosh, well, there's not even supply of crawdads around here, for one thing. So when you think about crawdads, what's one of the
the constraints of eating crawdads.
Very little
Take a
meat
long
right
time
now.
to put
You got a brick.
Yeah, you have to separate the head from the tail, you suck out the head, you peel the exoskeleton off of the tail, before you finally get to this little pile of nothingness that is the back end of the crawdad. There's a lot of handling time associated with eating crawdads. How does that compare with popcorn shrimp?
Poorly.
Popcorn shrimp, they've already been shelled, they've been fried, they're small. You can eat them literally as fast as you can chew. One of the nice things about crawdads is you can spend a lot of time eating crawdads before you finally get full because of the significant amount of handling time that is associated with them, which is great if you're sitting around with your friends on the weekend after finals are over. But it's not great if your goal is to get the most energy, nutrients, et cetera, out of the food that you're eating. You would choose popcorn shrimp over crawdads because popcorn shrimp have nominal handling time. Crawdads have significant handling time. So when we think about what you choose to eat, you can think of it in terms of how fast am I getting what I want out of the food that I'm eating. And so this would be a situation where the currency would be how much energy am I getting out of the prey that I'm eating, given some amount of handling time. So energy per unit time, once again, the currency is rate of energy gain. So we've defined what the currency is. If we have two prey types, there's a large prey type and there's a small prey type. Each of these has a certain amount of energy that is associated with them, and they have a certain handling time that is associated with them. You might think that large prey would be harder to handle simply because they were larger. And so while you may get more energy out of large prey, you might also spend more time handling that prey, such that it could be that large prey and small prey are equal in terms of the rate of energy gain if the proportion of energy and the proportion of time handling scales across these two types of prey in a way that is kind of linear. So let's assume though for now that you get more energy per unit time out of large prey rather than small prey. And so if the rate of energy gain for large prey, given some handling time for large prey, gives you more energy than the rate of energy gain for small prey, given the handling time of small prey. When it comes to prey choice, what should you eat? You should really eat large prey all the time. And when you come into contact with small prey, what should you do? Just reject it if you have the option of large prey. Now, this is something of an artificial sort of situation, because what I haven't told you anything about at this point is the rate at which you encounter large and small prey. What if you encounter large prey and small prey at the same rate? Go for large prey, because you know that if you see a small prey, you can not eat it because you know that large prey are coming down the pike. But this time between when you encounter large prey and when you encounter small prey becomes important. So the search time versus the search time for small prey. So the search time might vary by prey item. This becomes important, because now you have to include not only what is the amount of time that you're going to be spending handling prey, but you also have to think about what's the amount of time that you're going to also be searching for large prey if you pass up small prey. And so what ultimately happens is the combination of search and handling time becomes important in making the decision as to whether you should eat only large prey or mix between large and small prey. But that mix is going to be determined by what's the overall cost of handling
search. So large prey are more profitable, so if you encounter prey 1, you should just always eat prey 2, or eat prey 1 rather, but if you encounter prey 2, you should only gain if the gain from eating is greater than the gain from rejecting and searching for the more profitable prey 1. And so search time becomes important.
Is that H supposed to say H1?
Or H.
The first one.
Oh, it is supposed to say H1, yes. 1 is large prey, 2 is small prey. Yeah, it's correct here
Yeah.
and here.
So if you were to add search time into that, would you just, or factor it in, would you just add it to the handling time on farms with the E1?
Something like this?
Yes.
So this is the situation where this is more efficient than this, and you should only take 2 if the search time is significant enough that it reduces the overall rate of energy gain from large prey below a level of eating prey 2. And so if search time adds significantly to the total time, it reduces this rate below the rate of energy gain from eating prey 2, in which case you should eat prey 2 when you find prey 2 and prey 1 when you find prey 1. Small prey, large prey with search time included. So you shouldn't be a specialist, you should be a generalist if search time is significant. But once again, the particulars of the amount of time that you spend handling and the amount of time that you spend searching are going to ultimately determine whether this inequality is satisfied or not. So prey choice depends on the abundance of prey 1, because the abundance of prey 1 affects the search time associated with prey 1. So this makes 3 predictions. You should specialize on prey 1, or you should generalize. Those are your 2 choices. You should never specialize on prey 2, because it's the less efficient of the 2 prey types. The decision on whether to specialize or generalize depends upon the search time for prey 1, but not the search time for prey 2. And the shift from specializing to generalizing is sudden and occurs when the search costs for the more profitable prey exceed the gain from eating the less profitable prey. So when you switch from one strategy, specialization, to the other strategy, being a generalist, should be sudden. There should be a solid break point there. And that break point occurs when this goes from being less than that to this being greater than that.
So we expect animals to just all of a sudden come to this realization and just start only exclusively eating prey, a different prey?
No, they won't. No, it'll be, so yeah, if they were generalizing, if something happens, so this happens in lizards. Let me see if I have the data. I can show you. This was an observation made by a guy named Eric Pianka back in the 60s and 70s. Eric Pianka is an ecologist. He's an emeritus professor now at the University of Texas at Austin. I had a student named Daniel Biddle. I doubt that any of you guys know him. He's too far along. But I don't have it because it's on my hard drive. So Eric Pianka was a foraging ecologist. He was a lizard ecologist. He was interested in lizards in Australia, Southern Africa, and the deserts of Western United States, the Great Basin Desert, the Kalahari Desert, and the Great Victorian Desert. And what he observed when he was looking at the stomach contents of lizards is he observed that he would occasionally run across a lizard, and that lizard would be chock full of termites in the gut. And so normally termites are kind of a pain to eat because one, they are encased in a termite mound, and you have to break through the termite mound to get to them. And if you have little weak lizard legs, you can't break through the termite mound very easily. The other thing is they also bite and they excrete acid, and so they're also kind of unpleasant to eat because of that. They have big pincher mouth parts. And but there were some lizards that he would find in his collections, in museum collections, where a lizard would just be totally full of termites. And he chalked this up to these lizards must have been collected during termite swarms. In the life cycle of a colony of termites, they get to the point where it's time for them to fly off and reproduce and found a new colony. And when this happens, this is oftentimes brought on by weather, oftentimes brought on by rainy weather, and there will be termite swarms in an area. All these termites from all these termite mounds take flight all at once. They breed in the air, and then the females come back down to land, dig into the ground, and start a new colony. And then all the males are all over the place and perish ultimately. But during these times when these termites are swarming, every animal in the landscape has a super abundant supply of termites. And so while lizards would normally partition the prey, there are some lizards that are scorpion specialists, other lizards that are termite or ant specialists, and then other lizards that are just kind of generalist in their dietary preferences. All of a sudden, everybody in the community is eating termites. So when I was a graduate student, I went to Galveston, Texas to look at competitive interactions between these two species of geckos that live in Galveston on the docks there. And we collected a bunch of geckos, we brought them back to the lab, we opened up their stomachs, we counted the number of prey items that they had in their stomachs of different orders of insects. And what we found was that the two species where they occurred together had very dissimilar environments. So when they were in sympatry, so when you think about the distribution of two species, this is the distribution of species 1, and this is the distribution of species 2. Individuals that live over here are allopatric to individuals that live over here, but where the two species live in contact with one another, this is the area of sympatry. So what we found was that species 1 and species 2, when they were not in the presence of the other, had actually very similar diets to one another. These guys' diet was similar to these guys' diet. But when we looked at species 1 and 2, where they live in contact with one another, we found that their diets were different. Because presumably they were competing with one another, and in the process of competing with one another, they were dividing up the prey community that they had available to them. So we did this, these are two introduced species, and we did this in 1991. And what we found was that these two species appear to be competing with one another because of their dietary choices in sympatry were different and non-overlapping compared to where they were in allopatry. And we predicted that what was happening is one species seemed to be moving into Galveston and was displacing the other species. And so we made predictions that because they appeared to be competing with one another, that the one that had been moving in was apparently displacing the original species that was introduced there back in the 1950s, that would continue happening, and this more newly introduced species would continue moving into Galveston, and as it does, it displaces the one that was already there. And then we all went off to graduate school and got jobs and never went back. And so Daniel Biddle, who was a student here, I think he graduated 3 or 4 years ago, I proposed to him for his senior thesis, we should go back to Galveston after 25 years and see what happened. So we trotted down to Galveston, we got there. Over the 2 nights that we were there, we collected about 100 geckos, we brought them back up here, and we started cutting open their guts to see what they had eaten. And the problem with that was that while we were down there, there were a bunch of termite swarms. And I said to him, this could be problematic. And he's like, why? Well, because during termite swarms, this guy named
Bianca proposed back in the 60s and 70s that during termite swarms, everybody just eats termites because they're super abundant. And so we get back up here, he starts opening up all of the guts, and guess what? There's just nothing but termites in them. Just gut after gut after gut after gut after gut after gut of termites. 100 lizards, and almost all the prey items that we found in the stomachs were termites. Which was nice because we confirmed this idea of Bianca's from the 1960s and 70s, but it was bad because we didn't actually get to ask the question, are these two species still competing with one another? Because on those 2 nights when we were there, when there were a lot of termites, they were clearly not competing with one another. They were not competing because there was a huge amount of this normally difficult to access prey resource. So when you think about prey choice, termites are not a great prey item because, especially in Galveston, they're in wood. And a lizard can't break open the wood and dig through the wood. These are Formosan termites, another introduced species. They can't dig through the wood. They're tiny little geckos. They have weak little toes. And they can't dig through the wood to get to the termites. And so the cost associated with getting access to what would normally be a high energy prey item, because termites are soft bodied, they have a lot of fat in them, they're a good energy source. But the handling time, the time that you would have to spend getting access to them is huge. And so normally you don't eat termites unless they are way easier to get to. And as soon as they start swarming, you've reduced the search time because they're really accessible, and the handling time is probably very similar to other insects. Yes?
Okay, so they can't specialize on prey one, so wouldn't that mean that they're forced to specialize on a different prey? And mine is like a very convenient swarm of termites, and in which case they could flip back?
So in this case, the termites would be species 2 because the energy that you gain from them is dwarfed by the amount of handling that you would have to do to gain access to them. And so in this case, what happens with E2 is the handling time goes way, way, way down, which then converts it to this. Presumably nothing has happened to all of the other prey items in Galveston, Texas. They're all still the same. In this case, what's happened is this thing has dropped to practically nothing. Because trust me, they're flying all over the place. We have headlamps because they're a nocturnal species, and we need headlamps to see them. And termites are attracted to lights, and so we were constantly having termites flying in our face. So what's happened is the abundance of this prey item has basically reduced search and handling time to practically nothing, which makes them the most valuable prey item in the environment, and then they just eat the hell out of it. So the shift from specializing to generalizing is sudden and occurs when the search costs. What was I saying? Well, I don't know why I got on that. Oh, prey choice depends upon the abundance of prey. And so when prey are really abundant, that shifts this thing. Because what it does is it affects search in this case. And so you went from, in this case you shifted from taking a generalist approach to specializing on this one prey item, because suddenly it's super abundant, low search time, low handling time, which makes it much more efficient from the standpoint of rate of energy gain per unit of time.
So in these circles, you're saying abundance is higher when the circles aren't together?
Those circles?
Yeah.
No, this is just their normal distribution. But here, they would normally partition prey because they're competing with one another, and so one species forages in one part of that environment, another species forages in another part of that environment. They divide up the vertical space in such a way that they're not overlapping in their micro-distribution, and as a result of that, they eat different prey. As a result of partitioning the prey, they reduce competition so that they can both coexist. They don't have to do that when
they are separate from one another. They can eat whatever they want because they're only competing with other members of their own species for prey. But then if you flood the environment with one easily accessible, super abundant prey source, everybody, everywhere just eats it because of prey availability. So this is an example from your book. When you look at profitability of crabs eating clams, eating mussels, you see that there is a peak profitability where as the size of the mussel increases, you get more energy out of the mussel, but also as you get larger and larger mussels, those mussels have thicker and thicker shells, and so there comes a point where handling begins to take a toll on the amount of energy that you get out of them. This is in joules per second, amount of energy per unit time. And the reason that this curve starts to dip down is because while eating a large mussel, the large mussel has more energy, it also takes more time and energy to get access to the energy that is in those large mussels. So there's an optimal size prey that you should be eating if you are a crab based on the amount of energy that you get out of each of those. And when you look at where that occurs, it occurs at about 3 centimeters in size. And when you look at the distribution of what crabs do eat, you see that there's a peak here, and that peak falls a little below what the optimum predicts. So once again, an optimality model would predict a size of about 3, and while it qualitatively holds, there's this quick fall off at the high end of mussels, it's still below what the optimum would predict. So you get good qualitative match of the model to the data, you don't get great quantitative match of the model to the data. And this is a common theme. Another example that they talk about in your book is when they used Paris Major and gave them access to large worms and small worms rolling by on a conveyor belt. This is one of the things that behaviorists do oftentimes is they invent arcane ways of testing things. So you have a bird, it's sitting here, and worms are coming by on a conveyor belt at a certain speed. Some of the worms are large worms, some of the worms are small worms. If a large worm comes by, you should always eat the large worm because it's the larger worm, it's the more energy efficient thing to eat. But if a small worm comes by, you have to weigh what the profitability of that small worm is relative to when you're going to see a large worm again. Because when you start eating a small worm, if a large worm comes along next, you're in the middle of eating the current worm and you don't have the opportunity to eat the large worm that rolls by on the conveyor belt. It goes by on
Just drop the small one.
Well, unfortunately you could, but oftentimes you have it in your mouth and these are coming by on a conveyor belt and you have a small window of opportunity to get it because these things are slidable and you can change what the window of opportunity is. So you can do a couple of things. You can change how fast the conveyor belt is going, you can change how big the window is, and because you're adding the worms, you can change the ratio of large worms to small worms. So you can control all of the aspects of decision making that a bird might need to make. The problem with not having hands and being a bird is you're eating with your beak, you're also capturing new prey with your beak. So once you start handling one prey item, your beak is kind of occupied. And so it gets back to another one of the assumptions of many of these models. The activity of feeding is exclusive of searching and capturing. So if you're feeding on something, you can't be simultaneously searching and capturing because you're already occupied in the act of feeding. And it seems like an unreasonable assumption, but it actually turns out to be true for many organisms. I studied, for my dissertation, I studied the foraging behavior of an animal that could do searching and handling and eating all at the same time. And I was actually interested in how being able to do those things non-exclusively affected foraging decisions. Because spiders, spider would catch a cricket, stuff it in its mouth, start eating it, and then continue searching, and then when he found another one, he would just grab it and stick it in his mouth and start eating now 2 crickets at once. Well, that changes one of the assumptions of the underlying model, which is that those 2 activities are exclusive of one another. So we'll continue talking about this on Friday.
Oh.
Target lines, and generally you would, well, so it's, you specialize on the one that is the more profitable one.
It's not too bad.
At that time, you can see where
That class was just like.
you eat something,
class,
you eat more than
questions for
one
30 minutes,
type of
and all of the questions
So
were-
a specialist would be a person who goes to
And
the
like
for
all of the
and
answers
all of
are
that
vague.
stuff,
I'm like,
all of that
stop
person
asking
eats
this question,
is
he's not gonna tell you.
fried chicken.
It's not that much.
Doesn't eat
Or
beans,
like
doesn't eat
random,
fish,
very
doesn't
off
eat
the
banana,
wall, like
pudding,
questions that
doesn't eat,
were supposed to
goes
be
there,
impressive
eats some fried
to
chicken,
both.
leaves. A
A
journalist would go there and have,
And then
you
we do
know,
an activity.
fried
where it's
chicken
like,
leg,
oh, if
and
you're a
some
bone in this
macaroni and
region,
cheese,
over there, if you're in this
some
region. And like
beans,
then the class
some
in it,
banana,
we like did that.
pudding
for 15
afterwards,
minutes. And I'm
that's a
like,
generalist.
Then there's a list of
So-
like 5 pages long, bones and like
Think of it
those
that way.
characteristics.
The
that you
specialist
know,
is something that only
so
eats
it's
one
just
type of
based on,
thing.
like- But in class, all I did was show you what you did was part of the semester.
Is the switch from being a specialist to not being a specialist, being a generalist.
And that's when either A, either
And when the big prey is not available, that means that the search time between when you find one big prey item and another big prey item is getting longer and longer and
that
longer.
would make you a generalist.
That would make you a generalist because when you do come across small prey, if they're more abundant, you encounter them more often, so their profitability goes up because of the long stretches between when you find larger.
And that's why search time is the.
That's why search time
That makes sense.
for the
Okay.
profitable prey is the thing that matters.
Okay. In that prediction, got it.
Yep.
Good.
What?
No, they're foragers. Or predators. Yeah. They forage out for their food. And they scare them. Real question is, what does that hawk prey on? Maybe.
Squirrels and food.
Since it's heavy beast.
He's top dog.
That thing could have started that powerful. Should have shot.
Oh, there's a possibility
Uh-huh.
I might not be here on Friday because